Welcome to another small, not another, basically the first um, game, remake project, completely on video. The idea is basically to, take an old game which is no longer playable and redo it on the OpenRA engine, starting from reverse engineering the assets, implementing the asset loaders, and getting in-game without the polishing, of course, because a full game would be, I don't know, maybe I will do the full game. Um, if I do, it will be a lot more videos. So, anyway, um, first of all, let's think about which game we want to port. It would be awesome if we could port a game who is no longer playable. There are a few games actually who are still available to buy, but yeah, they are basically not playable at all. Let's hop over here to my good old games account, and we have Earth, Earth 2140. This game is basically an old school RTS. It would very nicely fit into OpenRA. We have some nice shiny explosions. If I see this right, let me see. Yeah, they use some different blend modes because they are semi-transparent. Um, we have selection boxes. We have a sidebar on the other side. Okay. We have power. We have cache. Yeah, we have nice graphics. Um, so it was an awesome game back in the days when it came out. The problem is actually that the company tried to port this game over to Windows platform from DOS, and accidentally they broke the AI. So the AI will just attack you with its initial forces, but it won't produce any new units. Um, so basically, the campaign is very easy to finish, and remember the original game was sometimes very brutal hard. So yeah, would be nice if we could revive this game. So first of all, I'm going to install this now. Yep. Um, Also, the multiplayer part, I'm not 100% sure. I need to look in game for that, but it's very likely that it is IPX only. I'm not sure if it has TCP support, but online play would be a no-go. Um, Maybe with some VPN software. Yeah. Anyway, okay, we got it installed. It's not that big. It's an old game. So let's search for this. Where's my games? Earth. Here we go. Um, yeah. First of all, what we can see actually is we have a movie folder. The movies are plain MPEG files. Nothing special in here. Music in a generic format, so there's no need to reverse engineer that. We just need an OGG player, and that's it. What else do we have? Let's start this by file type. Of course, we have the executable for the game and for the uninstaller. We have some third-party libraries, which are basically the C runtime environment stuff, OGG player. I think SDL should be used as the renderer and maybe the sound engine too in combination. Likely. The MPEG playback. This is very likely related to the OGG file. Installers or uninstaller information. Okay, good old game stuff. Icons, just good old games. Blah. Then we have some PDF files. Um, this is also called GUG game script. So something GUG related. Here we go. So everything we had here is pretty small, 7 megabytes. So this won't be the full game, and this on top is just movie and music. This is basically what's interesting, because this contains all the game assets. So we now have identified which files we want to read. The first thing you actually have to do is to reverse engineer these files, because it's not like do I need to open Photoshop, Paint, 3D Studio Max, Notepad, or whatever, and drag it in the correct application, because no application will be able to read these files. They are, yeah, basically made for the game. So what I know is actually that FLC stands for Autodesk Flick. So these are in-game animated images, like a GIF. I'm pretty sure there were some in-game wireframe animation of the units where they were just rotating. I'm pretty sure this is in here. Yeah, the font file is very uninteresting for now. Graph might be the menu graphics, not sure about that. This is very likely, of course, the level stuff. Because we know there is an add-on, there are two add-ons actually in the game. It might be possible the add-ons are in level 2 or in this mission pack files. I don't know. But now it's more likely they're in here. So okay, another menu files. So this might be also menu, of course, menu related. Mix. This sounds interesting. The chances are very high that all the assets we need are in this file. Pyro, I have no idea. SMP, my bets are very high that these are the sound files. But okay, let's start. The good idea is actually always to start with the smallest file, this one. The reason is we know this is all the same file format. But if we take the interesting files like here, or the big files at first, we have a lot to scroll and a lot to be, can be done wrong. So you basically start to reverse engineer this file. And if this works out, we will try to use our logic on all the other files. And yeah, if it works out, then we should be able to, basically read all these archives. We can be pretty sure these are archives because, a game must consist of a lot of assets, a lot of sounds, and a lot of images, a lot of metadata. Actually, sometimes they are hard-coded in the executable here. Stuff like how to put together specific images to a unit, unit stats, all this kinds should be in here. Yeah, and let's start. So the first application I want to use is this 010 editor. It is basically a hex editor, but it's more than that. Because actually, if you look at this is what most people probably have seen already. And you already notice there is a pattern here, which is what we're actually going for. Patterns are actually nice because you can see there is something here, like, hey, here's mix file, here is entry. Oh, you look at this here. These are file names actually. There's this folder fonts, and there's a file in here, and another one, and another one. One of the most important thing when reverse engineering a game is actually to have a good eye for patterns. Because mostly when you get compressed data like this, it's very likely we won't be able to read this at all, or maybe just with a lot of work. But I don't care about what's in the font files. If we can manage to read this, it's okay. If not, it's also okay, because all I'm interested in is to get this this archive read. So okay, now let's come to the more important thing, or more interesting thing. Actually, let's put this here. This editor supports templates. Okay, let me do it a little bit smaller. Okay, this is a standard hex editor. It shows basically 16 values per row. So what's nice about this editor is basically that I can actually say, okay, we start here reading, and what we can see here is there's a value with it's a size of 4 bytes. Why? Because here's the next value with a size of 4. It is filled up with zeros. The next one, the next one. This is what's called the endianness. Basically, numbers can be written like here 1, 2, 3, 4, 5, but also 5, 4, 3, 2, 1. It depends on which direction you start reading. If you read from the right, this would be the same as if you read this from the left. It's the same what happens in binary files. They are mostly, it's very, very likely you need to flip whatever you read. Sometimes even strings. So this string's not, obviously, but sometimes. So let's start. We know here is something. This here, what I've selected, is 1 byte. 2 bytes are called a short, 4 bytes are called an int. I think most of you are familiar with that. So the nice thing about this editor is actually we can tell int something nice. Let's start by saving this. Yeah. And click run. Now actually we see here we have something nice. Even if I click away, I click here, there is something nice. So let's do another nice thing. Go. And here we go. We have 2 values. We can click them. We can see their value in a normal decimal representation. So, of course, we have this as help here on the right, where you can see here as a byte, as a short, an int, a long, whatever. But this is the more interesting thing. One thing which is always nice to do is to set the background color. Come on, 2 likes. Let's take red. Why? Because we can always see what we have already read. So we will start here. The interesting thing is we have some numbers here. 1, 2, 3. So let's do this. Let's call this header. I will call unknown things usually unc. I don't know why. I'm just doing it. So we have 3 of them. Here we go. We can open this. This is the first, the second, the third. Then we have some zeros. Then we have another value. 1, 2, some zeros. What we are trying to do is actually we need to look at this and try to create a template here which basically starts reading here, reads all the file down, and exactly ends here. Basically, yeah, the same way as the game reads this file. There has to be some mechanic to read this. Otherwise, yeah, it would be just random trash data, totally hard-coded. There are actually, I found one game who does this. Basically, it had a huge image with a width of 256 pixels, and everything was underneath each other without any metadata. But yeah, even that was doable. So let's look. We have some data here, obviously. And one interesting thing is actually what we notice is there is a 4 and another 4. Same as here, same as here. So every 4th line seems to be, oh no, not the 4th. This one, 1, 2, 3, 1, 2, 3, 1, 2, 3. So we have some kind of pattern in here. So what we can do basically is to adjust this. Let's take 32 per row. You see, this is getting interesting. Let's use 48. Aha! This looks more like a pattern. It's now in a perfect column. So what we have here is actually interesting data. This is very likely interesting. Then we have a C, whatever this C actually is. Then we have some file names, and yeah, then comes another data format. As we can see here is that the 4 fits here, 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 here. It doesn't fit on here anywhere else. So yeah, it is very likely that this has to be underneath each other. So we have one thing here, which is repeated here, which is repeated here, and so on. There is some kind of pattern. So if you look at this, we have 11. How many entries do we have here? 1, 2, 3, 4, 5. It's not 11. But actually, we are almost at half. What would happen now if we change again this to half the width? You see, it's still somehow a pattern. It's not like bad example. It's not like I can't find an example. Yeah, like this weird random stuff. So this looks pretty good. And actually, if you look, this is here's where the text starts. Here. So we have this block, which is basically 1D if we reverse it, and the number gets larger and larger and larger, except this one. This one somehow just doesn't fit. But that's okay, because the pattern basically repeats till here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, interesting wise, we have an 11 here. We have exactly 11 rows matching this pattern. So what we now know is, we don't know what this is, but we know, let's call this Ank A. And let's call this number of Ank A's. So we are taking this first number here, and now we need to read Ank A's. So let's define how an Ank A looks. So we have an Ank A. Right. An Ank A has basically 1, 2, 3, 4, 5, 6 values. So let's call this again 1, 2, 6. And now we need to read this exactly this times. So this template is actually allow looping over variables. However, we need to define this as a local, because otherwise it will read another int. Like this notation basically means read 4 bytes and store it in this. So okay, now we have a local variable which we can use for looping. So okay. And inside this we just say we have something of type Ank A, and let's call it Ank A. Go. Okay, this pattern is read. We have several Ank A objects here. What we know is actually we have 2 numbers. The first one, let's comment this, is increasing. The second one is not increasing. We have the 4 things here and different sizes. Actually, very different sizes. As we know, this is a container, and it has to actually include files, as we can see here. This information is very likely fitting to a file. What do we know about a file? A file always has a file length, and it's very unlikely that all the files have a length of 0. Of course not, because there's data here. And this here also, that's not a file length. It's very weird stuff. So that the file length is actually increasing is possible, So we have two candidates. I'm actually sure it's not this, but I will explain this later. So let's say we have two candidates. So let's tell this. Okay, this could be the file size. Come on, today isn't my writing day. And another one. What we do know is that we get 3 times all 0 stuff. Okay, now we have some weird value. It's also increasing by the number of 17, sorry. Not always. This is plus 16. It's is weird stuff, but I have quite an idea what this could be. So the next thing we basically want to know if this is the number of files and this are information about the files, we can basically rename this num files. And we can call this a file. Okay. This whole WD file is basically one large file, which includes several subfiles. So how are we now supposed to get more files out of one file? Of course, somewhere in this one file starts, and when it ends, the next file starts. So there has to be some information where a specific file remains in this container. Because if this is a file, and this is a file, and this is a file, and this is a file, the number has to be increasing, which perfectly fits to this. So it is most likely that this is the file position. And then we have this candidate as the file size. So this is basically filled up by a number of zeros. The next interesting thing is actually here. We are now here. We get a C. Remember, on top here we had a B. This C basically tells us, it tells us nothing because it's the highest byte. This is an interesting thing because it's not that the number 1, 2, 3, 4, 5 will be 5, 4, 3, 2, 1. It's actually grouped into 2, and these groups are not rotated. So 1, 2, 3, 4, 5, 6 will be 5, 6, 3, 4, 1, 2. This might be a little bit, weird, but you get used to it. So actually, as we can see, this is the highest C. So this is very unlikely something about the number of files. But what we know is that this is followed starting exactly here with file names. The last file name ends here, and then we have here is actually something which we cannot see on the right because there is no proper representation of these numbers, but there is something here. But we have this block. And now is an interesting thing. Okay, this block. If you now look here at the select size, we actually see it has a size of C, 0, which is this. So basically this means length of all file names. So we know after this pattern we have this. You know what? Let's change the background color here. So this was about the files, and now let's use green. Because developers love ugly colors. Red, green, and blue are the only true colors. Yeah. Now we have some file names. Some of you might actually know that a 00 byte should it's not, it hasn't a value exactly. So in a string, or in other words, in a text value, there is nowhere a 00. It's mostly used as a terminator, basically telling that something is ending here. If we look at this, This is a string, and then we have a 0. A string can't contain a 0 because a 0 byte is always the string terminator. So we actually have information here where, yeah, where the string stops. Another interesting point is if you now look how many bytes we have selected, hex 11, and we now look at that the second file in this table here, the first one has 0, the second one has 11. I'm pretty sure the next file name will start on 22. So let's see, we are starting at fonts 22, and now 32. Yep, 32. So we know what this is. This is basically the file, let's call it file path length. Okay, and this is unused crap in the middle. Well, in this file unused, it might be possible that we actually need to read this files later, but yeah. So for now, we have a very easy file setup. Basically, we know now where a file is, we know how big the file is, and we know its proper file name. So what we now can do, actually, after we basically have this chunk here, which basically says, okay, this many bytes do we have? Let's see. We are now here at position 1D0. And if you look at here, this is where the first file starts. So yeah, this is the first file. To be specific, it's the peri12.curve file. And actually, if we go to yeah, we want to know if there is some information behind the files in this file. So this is the file size, this is the file position. So we basically go to FB95, which is this position, and we need to check for EF4A. So let's do this. File end EF4A. So yes, the last file ends here. There is no data behind. So basically, this is a very easy format because we already have basically the whole, yeah, format. Oh, and this is the mix file. Interesting. This is the file header of the next file we might want to decode. And actually, yeah, it's called new mix, this file. So what we now want to do is, yeah, let's assign this one too. Basically, we now need a code to start here, read this number, read this blocks, and we basically know from this number where this ends because this has a fixed size. So what we can do is actually wait, fat pass length. No, this is not a length. It was an offset. So what we basically know is that we have B files, so 11 files, which means we can basically tell the file how many files there should be. I think the syntax was something like this. Oh, please don't crash. Yeah, it was correct. So now we can use num files in here. And we have this offset. So what we can now do is let's store this. Original position. Yeah. What we can basically do here is first we store the position. So we continue reading where we left the last time. So hello, tell me where we are. So file tell. Then we are basically seeking for here. This is where we want to start with the first file. So we have the number of files multiplied by, yeah, how many do we have? 1, 2, 3, 4, 5, 6. So we have 24 bytes. Would be this part plus 8 because we have 4 in the front and 4 bytes here, which contains some other data. So, and now we should always be here. And now we have to add these values, which are basically pointing to the individual file names. So we will also do this. And now we are at this point where we should be able, I think this program is able to read zero terminated strings. Let's just try it. File name. When we are done, we are basically going back to where we were to read the next file. So copy this, go here, go. Oh, this looks good. This looks very good. So the first file is fonts Perry 12. Second file is also Perry 12, but this is a PCX, which is a graphics file. So it's very likely every font always has a curve file, which is it's very likely that's the metadata for the specific font file. So where to find which letter, how many spacing it has. Yeah, just to generate, it's a bitmap font, just to generate, yeah, text in game. Another curve file, yeah. So if we now want to read the file, in theory, what we could do after this, let's do this here, is to go to the position where the file should be, which is the file position. And now we know the file data is actually, how much data do we have? Exactly this much. And let's make them we already had green. Let's make them blue. What did I miss? So, as we now can see, we are reading this completely. We're reading all bytes from all files. So yeah, we actually reverse engineered this WD file format. Nice! So now the interesting thing is, what we need to do is to test this on another file. The, for us, most important thing, let's start with this one. Because I have somehow the feeling this contains sound files. Okay, this is a binary blob. This is just, yeah, it could be an image, it could be compressed data. It has, I wouldn't say it is a pattern, but this could be a raw audio stream. So let's just try the same. Go. And we are done. Why? Because the file length is 0. That's an interesting thing. Which means that we cannot rely on this first number. Let's look at everything else. Okay, we have a lot more of offsets. So this file is definitely different. Let's try something else first. Let's try the mix file because this looks more like our old pattern. Click on go. No, on this one. Here we go. Yep, this works. So it's likely that this file is actually a completely different file format, but they still have the same file ending because yeah, they are actually very different. I can see some offsets here. I don't see any file names here on top, and I just see raw stuff. So yeah, it's just very likely these are file starts. So the first file starts at 0. Next file here, and the last file starts here. So yeah, that's actually very likely. There are quite some files who work like this. It's basically if you don't need file names to for sprites to identify that whatever. Some games actually KKND uses that or does it this way. It just has no file names anymore, but for the sounds, the files are just numbered. So this is sound file 0, this is sound file 1, this is sound file 2, or whatever. And yeah, that's basically the way how it works. And then the game just instead of playing a file by a specific name, like here when loading a texture from a name, it will just start here, jump. If he says, okay, give me number 16, it does 16 times 4, and now it just jumps on the right position wherever this is. Reads the first number. Okay, here I need to start, there I need to end. And yeah, that's it. The only interesting thing is such file formats mostly have two different ways to end. The first way is actually that the last offset is the file end, which is basically marking that it has to be read to the file end, and yeah, that's it. Sometimes it's like the file end is not marked, so there comes a 0, and which means start reading here and just read as long as you can, and then the file ends. Yeah, you know what? We should try this just once to show this. So we have a file starting at 0. That's actually interesting because 0 would be here. So it might be possible that this header block, because it is filled with zeros, has a fixed size. And it has a fixed size. This offsets are starting basically behind this block. Might be here. So where are we? We are at 400. Sounds quite good because for hex 400, which is 1024, and if you divide this by 4 bytes, we exactly have 256 entries. Remember, 256 56 is exactly 1 byte, or what we can store in 1 byte, 0 to 255. So yeah, it's very likely this is some kind of header. So what we can do now is just teach this extractor. Should we? Maybe not. Let's first look at the last one. It should be 19 to E8C, which is here. And to the file end we exactly have 400. So yes, this is not a start of a file. The last entry in this list, this is the file end. So this is the last file. It starts here, it ends here. So for now, let's just extract one of them and manually. Then we will. I'm pretty sure this is sound data. This just looks like it has no structure at all. And then try to import this in Audacity because it has a raw import feature. And if it works out, we know how to read the sound files. Basically, we just need to go through this 256 possible entries. Skip the first one because, yeah, if this is 0, it's using this pattern. Otherwise, it's num files here, and we are using this pattern. And yeah, okay. So this should be the last file. Okay, so we're going to 1909B9. Let's verify this, 1909B9. And now we need to add the 400. So this thing about this is hex. So if we add 1, this won't be 10 here. It won't be an A. This is 1, 2, 3, 4 here. So this is basically the point where this file starts. And we know it should go to the end, so let's just copy this bytes. Let's use a new file. No, not a text file. Paste this here. So this is the last file. We will now save this as last file raw, whatever. Actually, I need to download Audacity because I don't have this installed, but this will be quick. And why not? Let's use the zip version, so I don't need to download this stuff. Create new folders, call this Audacity, put this on the desktop because we are working on here. Extract all the stuff in here and start. Okay. Not the nicest program, but it works. So, okay, let's try this. Import audio. Okay, we need to import raw. So let's take this, and now we have to choose basically what kind of sound do we have. We need to guess, but as this is a very old game, this we need to, yeah, it's very likely this will be some kind of 8-bit, might be more, but let's start with, you know what, start with signed 8-bit. Okay, let's use the standard unsigned. We will try the others later. So there we have the endianness. Let's use the default because it doesn't care. We are using 8 bits, so we have 1 byte. So this is an interesting thing. Most games are basically playing sounds directional, most RTS games. So if something is actually exploding on the right of your screen, you hear the sound coming from the right and or from the left or whatever. Due to this fact, the game basically remaps the channels where the sound is played all the time. So it doesn't make sense to use stereos in those games at all. Also, we are talking about a very old game, so it's likely to be mono. Let's import this. And it's quite short, so I'm pretty sure the quality is worse than what we have here. Let's try it. Way too fast. So let's keep it as it is, and let's not try 44. Let's try just half of that. This sounds quite right. So yeah, the audio format is basically very simple. We don't need to make WAV files of that because in OpenRA all we need to do is basically create an audio loader, read the specific amount of bytes which we copied here, and just put the right format information in front of that, and we will have our final sound. What I'm going to try now is basically, as all the sound files are one after another, if we open the whole container in Audacity, they will be all played after each other, except for, of course, this block here, which is not a sound. No, here, this header block. This will make some weird noises, and basically, when he reaches this byte, he will start playing them properly. Okay, do I have this still open? Yep. Let's drag. No, doesn't work. I need to use the importer. So as MP0, and we know we had this import. Good. So a lot of sound effects.
Going, yes, defending, escorting, attack, target selected, entering, alright, recording.
It's still too fast. So this wasn't what we needed. Let's try this again. So it doesn't seem to use some, really. It doesn't seem to use a standard not bitrate. sample rate. Let's try something like okay, this sounds good. Let's try it here.
Attack, target selected, entering. Alright, recording finished.
Ready, waiting, going, accepted, defending, escorting, attack, target selected, entering, alright.
Okay, it still sounds not 100% right, but it's not bad.
Destroy. Target. Destroy. Reinforcements coming. Lack of cash. Low power.
Yeah. Okay, so let's just comment this here. So later when we port this to OpenRA, we will know what to do. So basically, if num files is 0, then okay, this is something we can work with. Let's trash the rest. Basically, I'm more interested in doing sprites as a start, because we can view them in the in-game asset browser, and the stuff like like sounds is something we can do later. Okay, so back on this file, still runs. What do we have in here? So we have fonts, we have, oh, SPR. This could be sprites. Very interesting stuff. We should extract one of them. Later we will basically read them all at once, but to reverse engineer the formats in here, which is a mix format, whatever a mix is. Okay, it's mix WD, so it's very likely that the mix container contains mix files. Yeah, we really should use one of them. I don't care about fonts. I have no idea what mix max is. Really no idea. But this SPR stuff is very interesting. Data B. Okay. What do we want to use? That's actually a good question. Should we use the... Okay, what could it be? Sprite B. Could be buildings. Infantry. Mission maps. O for objects. T for tile set. Okay, let's I think tile sets are pretty good if these are tile sets, because they mostly have images of all the same size. So this would be the most easiest thing to start with. So let's see if we can find this sprite T1. Should be somewhere. Oh, wow. Here it is. So basically, this is the file data. So we can just click it here, and let me say copy. As I said, we will do this later automatically, so we don't need to manually copy subfiles. Okay, store this here. Let's save this as, let's give the original name, just because we can. So save. This should be the file name. Where are you? There you are. Okay. Of course it's open. I just saved it. This is also a lot of information. It has an interesting pattern. So okay, this is what we can see basically there. It has a header telling that it's a mix file. It has some information, whatever is in here. Then we have entry. This is very likely a sprite container, and I hope it is a tileset container. We know that a specific container mostly holds more than one image. So every thing in here, I think it starts here after entry. So we have this weird offset. Exactly this much should be the, yeah, this block basically should be the information about where to find stuff. Because actually, if you look at this again, we have 160, 180, 1A. So it's again getting bigger and bigger. So these are very likely offsets. So this could be offset for all the sprites. Then we have PAL data. Old games usually use palettes to implement faction colors or whatever. So this is the color palettes. This is an interesting thing actually. We will try to read the header, then we try to parse the palette. How long is this palette? I have no idea. But after palette we have this. It's, you know what? We will start at the top. Because without the proper coloring I can't see a thing. So let's again start with this. Let's call this whole thing mix. So run. And we see nothing because it's a wrong file. So what we know is we always start with a specific, we don't use a char array because it is not zero terminated. This is a fixed size, whatever is in here. So let's call this mix file. Let's do it this way. And it should be 8 bytes if I see this right. Okay, 8 bytes. Now we have 2020. This is an interesting thing because 20 is a space bar, a written space bar. And actually, if we can look here, this could be an offset. This could be an offset because it has 3 or a number because it has 3 zeros here. So it's very likely this is actually this thing is has 2 space bars in the end, and it has 10 bytes. So okay, you know what? Let's instantly change color after that because it looks weird. Let's get to green. Okay, so here's actually something which is kind of big. It's actually 1F85E8. Is this even in the file? Oh, 1F8A08. Let me quickly notice this. 1F8A 1F8A09. The number was it the same? No, it was basically 1F85E8. So this, no, 1. But that's no coincidence, basically. It's very likely that the header again has a fixed size, and if we basically add the fixed size on this or subtract the fixed size from this number, we will get the opposite value. It's mostly like that in such files, because yeah, it mostly is. A lot of files actually contain their own file size. So when the without the header, of course, because the header is parsed and then everything else is basically allocated in memory. So they had to know the correct number of bytes they need to allocate. Okay, let's go on. We have this here. Let's call this. I will now call this Ang1, but it's likely the file data size. Okay, what else do we have? Now we have another number. I don't know what it is, but it has a number of 252. Then the next one is another number. It's 1057. What the fuck am I doing? Okay, go. Now we have all zero stuff. Okay, I can live with that. I'm just noting this like this, so it's I know it's basically 0 bytes not used. Then we have a 1. Okay. And then we have another one, which is 1052. Interesting. It's almost this number. And then we have entry. Okay. So let's go again for another color. Let's go red again, and let's call this oh, come on. Entry, which should be 5 letters, 5 characters. Okay. Now we have this. Yeah, these are offsets because they're getting bigger and bigger and bigger. How much do we have? Exactly this much, which is 3F0, which is 1008. We don't have a 1008. But actually, what we do know is actually the Windows calculator has an interesting option, which is basically called the programmer mode, where you can enter or basically convert between decimal stuff and hash stuff. We have selected 1008 bytes, however, and these are all integers, so we need to divide it by 4, and we have 252. Oh, interesting. This is this number. So these are the number of entries. So let's call this num-entry, whatever an entry is. So after entry, we can basically go again the same approach. I will be lazy. I just copy this. Okay, let's go over num-entry. And this is just an integer. As I don't know what this is, then let's call this entry unc1. Or it just has a number. So entry unc. Okay, here we go. So far, now we have a 20 PAL data. This is quite interesting. We have another 20. So there are two options. This is PAL data, or this is PAL without information, and this is data. Because we have a 0 here. So this might be the number of colors, and if the palette starts here and there is nothing in here, then it's basically empty, and then comes the data. Anyway, we don't know this. It's just an idea. However, if you now look exactly where we are at 420. And we have noted these values. And if we basically take this one and we subtract this one, we have 421. And we are here at, PAL data space. So yeah, here's where the stuff starts. And as we can see, is exactly as I said. This is the header, and it ends here. So for now, as we don't know how much bytes this really has, let's call this one PAL data. It's weird to have both, but okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 bytes here. Oh, and a space at the end. Oh, maybe it fits. Okay, here we go. I'm pretty sure. Okay, this is of course 0, which has to be this file here. So something has to start here. As I already noticed is actually we get six. If you look at these values, let me put them in one column. It looks a little bit weird, but actually if you look here, 2, 4, 6, 8, A, C, E, 0, and again. Basically, this is the lowest byte, so the number is basically this one. It gets larger on the smallest side by actually by 6, from 0 to 6, and on the biggest side by 2. So we have actually this is the number of bytes. Every entry seems to be the same size. So yeah, I'm actually absolutely sure this is a tile set. Okay, let's get back. The interesting thing is actually this number. It is weird, to be honest. However, can I open the second calculator? Ah, god damn it. So it has the same size. However, what we read here, it's not much. These are just offsets. This is just some metadata in the top. Let me once again look at these values here. They are 421, 41C. We are here at 421, yes, which is the first one. Or 421, which one was 421? This one. So ang3 is basically the data offset, because we know that it is. This is interesting. It's here. It should be 41C. Should be somewhere 41C here. So you see this, actually it starts with data. So I'm actually sure, because it points exactly in between that yeah, it's like this. So this is the palette offset. Basically tells where the colors for this image are, which might be a little problem because we don't have them. Wow. Anyway, maybe we don't need them, or maybe there's one shared palette in one of the other mix files. We will see this later. For now, we can just fill them up with a grayscale if they aren't in well, if they are using a palette. So this is likely then, as we know it has a size of 0, this might be the palette colors. So if this has a value later in another file, and it matches to the number of bytes multiplied by, I don't know, 2, 3, or 4, depends on the bit depth of the colors, then we will know that, yeah, it's just likely. Oh yeah, and this is basically what we just verified before. So this is the data size. Nice, we already got that. Okay. Now we know we have about yeah, it was about 8,000. So it's just likely it was this. No. How much was it? Here it is. No, here it is. This was the amount of bytes we had. And now let's check if I can open a second calculator. Yes, I can. Thank God. Okay, we can actually see data here, but this first, the start looks different. It actually has 40, 0, 40, 0, and then, yeah, we have the data mass. So, what we need to know, what we know is actually this should be an image. And an image always has two things, a width and a height. So we have 40, which is 64. Actually, most games are using a 32 by 32 or yeah, such tile sizes. So it's very likely this is the correct size. I will later do something like this where we basically go over all the index, but for now let's just hard code the first image. So because it only has one 0 filled up, it's a short. So let's assume it's the standard XY with height pattern. So this should be width and height, and let's make this green again. Here we go. So now if we subtract 4, but we had actually 6 too much if I remember right. So we have 40 by 40. You see, this doesn't fit actually because we have the double amount of bytes available. But as there was no palette, it might be possible that this whole image does not use 1 byte per pixel, but uses 2 bytes. So it's 16 bits per pixel. So if we multiply this by 2, we actually see the number is almost equal. We have just 2 bytes difference. So it's very likely this 2 bytes also are not part of the image. So what could they eventually be? Let me think. Sometimes sprites have an offset, so a center point telling the game, yeah, where the image center is. So the frames of a unit align properly. This could, for example, be it. However, I'm not sure if it is. So we need to check that. Yeah, how should we continue? I don't know. This is weird data. Sadly, this is 16 bits, and what I'm thinking about that, it might be possible that it's not possible. Sounds weird. To load them properly into OpenRA. What are we actually? What we could do is, yeah, what could we do? OpenRA allows to load 32-bit PNG files for the UI, but I never tried to do 32 bits for the tile sets because they're also using palettes, and I'm pretty sure that's hard-coded. You know what? I think we should swap the mix file. But before that, let me just show you one more thing. I actually wrote a tool once ago. I called it Pixel Magic. Don't ask me why. It's basically an HTML tool. It's yeah. There is definitely image data because I coded this because I made some helpers to detect what's in there, and we knew the tile size was 64 by 64, and here we go. As we can see on the top here, let's zoom this a little bit in. These are basically the data which we have read here on the top, the tables, you can detect them, and then we have uncompressed tile sets. And yeah, in as said before, 16 bits per pixel. I will load this definitely in another video. Okay, I will load everything in another video because this video is just about the reverse engineering. But I need to talk to the developers, or maybe I just should try it myself to get a implementation of of tileset which are using the full color scale instead of a palette. But yeah, it looks actually very nice. Okay, back to topic. Let's use another one. So if the T stuff is terrain stuff, I'm actually more interested in units. So we have terrain 1, 2, 3, 4, 5, 6. So it has 6 tile sets. Pretty interesting. Oh, what is it? This U. U could be units. That's yeah. Let's try this. So this pattern, and it's the second last one. This one. Okay. Copy, new file, hex, paste. And again, I want the file name. Okay. So before we, no, I don't know what that. Before we try this again, let's look at this U file here. So we definitely see a pattern. There is stuff in here, but it looks totally broken with the colors in 16-bit per pixel. So it is not 16-bit per pixel. So it might be possible that this time this thing is actually using the color palette. The question is, in which format is it? This was quite interesting. As we know, yeah, palettes contain 256 colors. This looks quite good. Of course, if we are basically reading 3 bytes. Oh, let's try what happens if no. This is definitely the palette format. But if we are reading 1 or 2 bytes off, the colors will be wrong. But yeah, this one has a palette. Nice. I'm pretty sure it has. Let's try this. No, let's try this one. Okay. Here we go. Entry, blah 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 blah. I know a lot of entry stuff. Here is aha. You see, there's no data here. There seriously is something here. And it starts with 000, which is black. And there are 3 channels. It doesn't have alpha, so yes, this 24-bit stuff is okay. So now comes the interesting part. We had this 0 here. How large is this block? Let's first check how large it is so we know how many colors there should be. This is definitely more than 1 palette. But yeah, we already knew that because of the image we just generated. So okay, let's go here. Still a palette. There is data. Here we go. We have 6,900. What the hell? Okay, let's check these numbers up here. It was hex 6,900, I think. Was it? Oh yeah, bytes. We need to divide this by 4. No, by 3, sorry. So this is the correct number. 2,300. And actually, if there it is. So this works nicely. Oh, so this actually is Ank 4. Yep. But that is actually not the number of colors because, as you can see, it's 23 and not 2300, which basically means 1 palette exactly has 256 colors. So these are 23 pallets. So this is the number of pallets, which brings us to an interesting point actually. This thing here is left. It is not one. It now has a different value. I'm not sure what this is, but I think we will find out. As this is between the num pallets and the pallet offset, it's likely pallet related. And we have multiple pallets, so it might be possible that this is some... Actually, I've seen this once in a game. I'm pretty sure it's something like this, if I think about it. Basically, we have multiple pallets in here, so every sprite has... Yeah, it basically needs a byte which tells the game which one of the pallets to use. And mostly pallets are registered globally in the game. And yeah, so a pallet could be in another file or wherever. So they are referencing it. However, if you basically have 2 pallets in one file and 2 pallets in the other file, and which one is then pallet number 1? So it's mostly that there is some kind of an index which has to be yeah. So it means basically the first pallet from this 35 pallets in here is number 45. The next one is 46, and so on. So I'm pretty sure it's something like that, but I will look at about that later. Okay, so back here. We have pal, and we need a loop. Of course, we need a loop. We always need a loop. We already have to find what I is, so let's go over the number of pallets. And now let's just... let's call this... can I do this? I think this application... I'll try. It might cause problems. So we have this number of colors, 3 bytes per color, and I will run and it will tell me, yep, it cannot generate multi-dimensional arrays. So let's make a struct, call this palette. So basically a palette has colors. It could be this, colors, and then instead of this, just do this. Here we go. And now data, yeah, it matches again. Woohoo! Oh, there are actually empty pallets in here. Interesting. Yeah. So we had data, and now we have width, we have height, and now we have, yeah, information. Basically, now comes the pixel data. And as I see this information, it looks like there is some kind of compression in this image stuff. Because actually when we look here, and we now know, okay, it has a palette, so it has to be 8 BPP. And we have a width of 50, so 5 times 16, so 80. We should be able to see something, but actually what we see is garbage. It's totally garbage. And this, for example, is interesting. Something actually, it's not just the width is wrong, because it goes to the left and then it goes to the right. This is basically caused by compression. Most old games are basically using some very simplistic compression to reduce the file size largely, especially by when you think about sprites. You think about an explosion, you basically have a round explosion, but images are always a square. So you have a lot of empty pixels in the edges. That's why usually sprites start to have some kind of mode switch. So first you get some skip this amount of pixels, and now read this amount of pixels, and now again skip this amount of pixels, and so on. Yeah, and as you can see, this basically is an image which has a compression, And on top there is definitely a pattern here of 2 bytes because we have color black, color black, color black. This is the header information about the compression, so it's very likely, yeah, this stuff. It could be something like, you know, this row has this amount of bytes, or yeah, something like that. So just information, or where does which pixel row start, could also be. But I think that would be the perfect thing for the next video. Yeah, we actually, let's think what we managed to do. We managed to reverse engineer the WD container format. We found out how the sound formats are working. That's pretty simple actually, and pretty stupid. Then we have the mix files actually, which contain, maybe we should rename this to, I think this is not a data or num entries, but these are these single images, so these are frames. No images. Okay, but we have the header of the mix file, which is not very complicated. We have the color palettes in here, if there are color palettes. If not, we know for the tileset, we now know that they are in 16 bits per pixels. So yeah, we know the palette format. We basically have the it's very likely the image size, and yeah, I think I will end this video. As I already said, next time we will continue here, and before I will do the next video in the next days, I think I will try to prototype, if it's somehow possible, to implement non-palette based tile sets, because that would be awesome in general for OpenRA to have some very beautiful tile sets. Of course, you cannot use any palette effect then on the tile set, but I don't. Yeah, if you know what you're doing, and that you don't need these effects, then I think it would be okay. Yeah, so alright, let's hope the next time we can get the tile set basically loaded and running in the game to build a dummy map. And if we have enough time after that, I will continue on quickly adding the sounds. Yeah, I know we are on the sprites now, but yeah. So we have map and sounds, and all we are missing are actually the sprites themselves. And then we will at last, do the sprites, because this will be the last chunk we need actually from all the assets. And if they are implemented, we will do some dummy actors. So yeah, we will base this upon. Let's first base this upon CNC or G2K or any of the core mods, and if all works out, we are going to basically, drag it out and merge this into a new mod SDK project, which is basically starting from scratch. Then, we will copy over the working sprite and sound loaders. Then make a small dummy map and see how far we can get. Yeah, so thanks for watching. I hope this isn't too boring at all, but yeah. Anyway, see you next time.